have three talks, one remote now and two on site after the coffee break. So the first speaker is Pablo, and yeah, please, Pablo, go ahead.
So thank you very much for scheduling also my talk earlier. Many people probably already heard part of this presentation in the SECAM school, but those who didn't, so this is about how we use machine learning to improve quantum chemistry and dynamics. Also, even though for people who attended SECAM meetings, so I will add more information about actually focusing our research rather than giving some lectures on the basics of machine learning. So what we do in this research, we improve and accelerate quantum mechanical approaches also related to dynamics. So we do this with our own atomistic machine learning suite, which we call MLAtom, and you can run even some simulations on the cloud, which has many more capabilities than just machine learning, also valence bond and energy decomposition software and so on. So I will start with a bit of advertisement that what is, for example, this Slack channel that or Slack workspace that you use, what this MLQC is. If you wondered, so this is something we started from in 2021. That was a symposium on machine learning and quantum chemistry. And for that, we created these many resources, also a website where we collect also videos and of the talks and organize other events. So now, obviously, this is a much broader scope. We also may include in the future quantum computing, because this becomes part of the quantum chemical research. And again, in 2023, this will be continued in Uppsala. So you're invited to participate, hopefully in person. We also have a special issue for sim collection in PCCP. So if you're already preparing some manuscript, please consider submitting it if it's about some insightful machine learning for physical chemistry. The deadline is basically before December. And also we have a book where you can learn more about machine learning in quantum chemistry. So if you like what we are doing, then you may also consider joining our group, or if you have students who are interested in continuing their studies, you can recommend our group. So Xiamen University is a bit far from Europe, but it's a very beautiful place, and chemistry here is also one of the strongest in China. So this is a good place, especially for chemists. All right, so what about dynamics? When we talk about machine learning for dynamics and quantum chemistry, then the question is actually what kind of dynamics we consider. There are many different types of dynamics, and machine learning can be applied practically in any of them. I will focus on three big types, which is classical dynamics based on Newtonian laws, and then trajectory surface hopping, quantum dissipative dynamics of open systems. And if you look at these classical dynamics, we need obviously to integrate Newtonian's equation of motion, which means we need accelerations, and for accelerations we need forces, which can be obtained from quantum mechanical calculations, basically using Born-Oppenheimer approximation, and that's why we call this Born-Oppenheimer molecular dynamics or ab initio molecular dynamics. And for this, we can use many different quantum mechanical methods. ranging from semi-empirical to density functional theory and ab initio approaches. All of them have the advantages and disadvantages. If you want to have more accurate results, then we want to choose very accurate ab initio approaches. The problem with them is that these calculations are typically too slow, and that's why realistic simulations mostly performed with density functional theory methods, which kind of have sweet spot between accuracy and speed. And if you need to perform massive simulations, then you can use semi-empirical methods. Now with machine learning, we already saw in many talks before in this conference and our school, we can substitute these methods with machine learning. So this is basically a game changer because it allows us to substitute expensive calculations with surrogate model. And this allows us to approach any accuracy you can afford by generating sufficient reference data. And you can even get like couple cluster accuracy and beyond if you have enough training data. The speed of it is usually slower than molecular mechanics because there are more terms to evaluate, but it's kind of competitive. Also, you can combine machine learning methods with quantum chemical methods, which has its own advantages. So then you usually have higher transferability, as we will see later, and at the same time, you improve accuracy of these approaches a lot. So you can do this for your systems, or you can also use nowadays for many purposes already, general purpose methods. So the pre-trained models or methods like combining pre-trained machine learning models with semi-empirical methods or DFT and apply them instead of conventional quantum mechanical methods. So, for example, this ANI1CCX, which was developed based on very long line and tree of these ANI methods. So it's started with Bello-Perinello approach. I will mention it briefly later. But basically, what we need to create general purpose method is to sample lots of configurations of different molecules. And this was done already 2017 at the DFT level of theory for many organic molecules. And this approach, like ANI methods, ANI1 here, approached DFT accuracy. Obviously, if you push it to coupled cluster, you can. So you just need to generate coupled cluster data. So that resulted in this approach, 2019, by this group and more people, and resulted in this ANI1CCX methods. Now what we did, we collaborated with part of this group, and we created combined methods, semi-empirical plus machine learning approach. And we call it AIKM1. So why do we need actually combining semi-empirical methods with machine learning if we have already such a good approach, right? The thing is transferability. So if you just look at accuracy and cost, then obviously ANI1CCX is pure neural network, so it's much faster. And it was trained on a couple cluster level of data, so it performs for many molecules and types similar to the training data quite well. And the speed is very, very fast. So the speed is high and the computational cost is low. So these methods are very good. But the problem is, as with any pure machine learning approach, transferability is quite limited. Even if you apply it to the same properties that you trained it for, it was trained only on ground state, neutral species. then if it's very, very different from the training data, it will break down, right? So you should be careful with this. On the other hand, a bigger problem is that if you try to apply it to something else like charged species or excited states, then it basically will not work. And that's why you need to train more, right? That's why by combining with semi-empirical methods, so we achieved the accuracy of coupled cluster, transferability of quantum mechanical methods. And this is, of course, increase the speed because we know the baseline is our semi-empirical quantum mechanical methods. But the transferability is improved a lot. And the speed is still very fast because semi-empirical methods are quite fast. And here is just an example. If you take C60 fullerene, and we do geometry optimizations at the IKM1, then it's 14 seconds single CPU. If you try to do some DFT without too large basis sets, so just take some normal basis set, then it's 30 minutes on 30 CPUs. And if you try to do couple cluster calculations, then even single points take like 70 hours. Now, again, this you can run even these calculations on the cloud now, and code available for downloads, so you can use it. Now, this approach is based on semi-empirical methods and neural network, but it also includes dispersion interactions. And this is because long-range interactions are very difficult to learn with neural networks. There are many approaches, but it's still quite a challenge. On the other hand, semi-empirical quantum mechanical methods do capture lots of long-range interactions, like electrostatics. But the problem is dispersion interactions. Both semi-empirical methods and neural networks struggle with it. Again, there are approaches to deal with it, but it's not that straightforward. So what we did, we just applied Grimm's latest generation of dispersion interactions, which is D4. And now we have a combination of these three components. Obviously, we need to choose a very good semi-empirical quantum mechanical methods, because the better our baseline, so the better our semi-empirical approach, the better will be quantum mechanical methods improved with machine learning. So we choose also state-of-the-art semi-empirical methods, which are called orthogonalization dispersion corrected methods. And their strength is that they solve many inconsistencies of typical NDDO based semi-empirical methods. So they include orthogonalizations, they include penetration integrals, also covalence interactions, and they are parameterized on both ground state and excited state and non-covalent properties, and solve some other problems. So if you take this approach, ODM2, and compare it to some older approaches, then basically across many properties, it was performing the best. Also for excited states, which you'll see very important later, also for dynamics, the performance is very reasonable. So these methods approach accuracy of TD bis-relief with triple zeta basis set, which is 1,000 times slower if you benchmark on vertical excitation energies of small organic molecules. So now, when we go back to construction of AIKM1, this is done using many steps and by carefully selecting all components. So one of the main problems is, of course, data set, right? So the better data set, the better quantum mechanical methods improved by machine learning. We took these data sets used to train ANI methods, so it's DFT level, almost 5 million geometries using both energies and forces, because it's very well known, and we'll also see later. If you include forces and accuracy of neural network potentials and in general machine learning potentials improves a lot. We take this data set and then we train neural network on the difference between DFT energies and these semi-empirical ODM2 energies, and also differences for forces. And after we train this on differences, so this is basically delta machine learning approach, we get our neural network with parameters. And we don't want to stop on DFT. So we want to approach coupled cluster accuracy. So for this, we have another data set, which is 500,000 data points, but unfortunately only energies. And here we use these very powerful methods, which is transfer learning, so that we take our neural network pre-trained on DFT, and then we use transfer learning to only optimize part of the parameters on the differences between coupled cluster and semi-empirical methods, minus also default corrections, dispersion corrections. And this gives us a neural network, which again, if you use this delta machine learning approach, corrects semi-empirical methods, and you add also dispersion corrections at the end. And then after you summing up neural network corrections, dispersion corrections, and semi-empirical predictions, then you will get energies at the EIKM1 level. So this is a really very powerful approach, and it's based on this delta learning approach, which is a very powerful way to combine low-level quantum mechanical methods and high-level quantum mechanical methods, and its power is illustrated very nicely on this simple example. So when you have this dissociation curve of H2, then if machine learning only sees part of this dissociation curve, then it will not be able to extrapolate very well. So it will not see that there is a minimum. So it will miss this minimum because it just doesn't see this pattern in the data, right? So it's pretty obvious that machine learning has problems for such cases. Now, if you take UHF, which is quite inaccurate approach, so if you compare UHF and full CI, the error is huge, right? So machine learning error has much smaller errors than Hartree Fock. But the problem with machine learning is that it does not follow correct physical behavior, while low-level methods like Hartree Fock follows correct physical behavior. So now we combine two bad approaches. So we calculate the differences between high-level and low-level, and then we train machine learning on this difference. And the differences are usually much smoother than the data itself, right? And if it has more predictable behavior, machine learning just thinks that the difference will continue being following this trend, and then it will correct according to this trend, and then you see this delta machine learning approach. So basically, after you take UHF and add correction with machine learning, so this blue curve is basically the same as the reference black curve. So this demonstrates why delta machine learning is working and why it's so powerful. So even in the cases when you don't have enough training data, it basically still works, because if you have good baseline, and we choose one of the best baselines from semi-empirical, among semi-empirical methods, then we will get better results. So transfer learning idea is related, but it's quite different. So here we also deal with several levels of theory. Low level of theory, like for example, DFT level of accuracy, and coupled cluster level of accuracy. So here, what we can do, we can train first on the low level of theory, and you can then here is again this example of H2. So if you look at the neural network predictions trained on this coupled cluster data, then it does not perform very well because there are not enough training points. However, if you then include more accurate data, and then you fix some of the parameters, then you can basically predict, so you can train only, you can fit only part of these parameters, and then it will preserve the overall function shape inherited from the lower level, and it will approach much closer the reference data and the high level. So it will just slightly improve. So this is the combination of both delta learning and transfer learning. And when we compared for many data sets, we see that this table is quite huge. So you don't need to look at all details, but what is very important that green is good and red is bad. So we color coded all these results for many data sets and many properties. And AIQM1 is green for many properties. Coupled cluster is obviously a very good approach. So it's green for everything we could calculate it. The problem with coupled cluster is that it's too expensive for many calculations, like heat formation, and because it requires also frequency calculations. So it means that we could only perform these calculations for some single point benchmarks. While AIQM1 can be performed for all data sets. On the other hand, these ANI1CCX pure machine learning methods cannot be performed for properties like excited state energies or charge species. That's why you see there are missing also entries. If you compare then AIQM1, like overall it's green, and it's definitely competing with many popular DFT approaches. Now, if we just focus on ground state properties for neutral compounds, which are heat of formation, reaction enthalpies, and energies, then you see that its performance is really excellent. So the error in kcal per mole for energies reaches chemical accuracy. So the error is less than 1 kcal per mole or close to it. But even for some difficult data sets, even coupled cluster doesn't reach, at least this kind of coupled cluster does not reach chemical accuracy. And also for geometries, you see that AIQM1 performs pretty well. Now, very important is not just to look at the tables, but also look at some specific examples. And especially for geometries, we found that AIQM1 is really performing very well. So this is an example on fullerene, for which pure machine learning approach ANI1CCX has a problem because it's a peak conjugated system, and then it does not distinguish that there are two types of bond lengths. One has some double bond character, another single bond character. And experimentally, you know that they are
Pavlo, we cannot hear you anymore, so it's frozen. So just wait a few minutes. We're trying to solve it. That's connection. From its side, maybe it's his side. Yeah, could be. Tu veux faire ça de son côté ou de notre côté? Ah, ok. Bon, ben, dans ces cas-là, on va. Ok, donc c'est de son côté. Bon, pas grand-chose à faire. Okay, we cannot hear you. We cannot see you either. On va essayer de se reloguer ou vous pouvez lui écrire. Ah oui, c'est vrai, on l'envoie. Non, il a disparu. Ah, c'est... Ouais, ouais. Tu peux essayer pour voir si... Ouais.
Test.
Moi, montre. Ouais, ça marche. Ouais. C'est peut-être ton micro qui n'est pas branché, Nina. Ouais. S'il est sur... à la base. Tu vas arrêter la session, ouais. Peut-être envoyer un message.